there she is. She's popped up. Okay,
Yeah.
so
Yes.
let's, I hope I pronounce your name correctly, Dr. Kwan.
Yes.
Your first name, Hatek Kwan, and you're going to talk about topographic effect of the Antarctic Peninsula on strong wind event. And please go ahead, and you have 10 minutes and share your screen, please.
Yes, thank you for your introduction. Is this look all right?
Yes,
We can
Yes.
see your screen. We can
Yes.
see your screen.
Yes, thank you. I'm Ha-taek Kwon from Seoul National University, and today I'm going to introduce the study about topographic effects of the Antarctic Peninsula on strong wind events. Let me start with the brief introduction to the background of this study. The King Sejong Station is located in the King George Island here and near from the northern part of the Antarctic Peninsula. And it has been operating for about 30 years from 1989. And on 7 January 2013, the strong wind event occurred at King Sejong stations, and it lasted for almost 12 hours from 6 to 18 UTC. And it was recorded as a blizzard with a daily mean wind speed of 16 meters per second in the weather report. And the figures on the right side here shows the time series of the observations for wind speed and the surface pressure like this. And we can see that the maximum instantaneous wind speed was about 42 meters per second. And the maximum hourly average wind speed was 21 meters per second. And the surface pressure shows the change in the opposite phase to the wind speed like this. As the wind speed goes up, the surface pressure decreases like this. Then how much this wind is strong? To check this, at first, we investigate the wind climatology at the King Sejong stations. Typically, the wind at King Sejong stations are weaker during the summer, with the daily climatological value of wind speed about 7 meters per second. So considering the daily mean wind speed of 13 meters per second of this strong wind case, it's very unusual. It's very unusual in the summer at the King Sejong stations. And this figure shows the frequency distribution of 10 minutes and daily average and daily maximum instantaneous wind speed for the period from 25 to 2015. And x-axis shows the group of the wind speed, and the y-axis shows the frequency corresponding to the s-axis. And first, looking at the maximum instantaneous wind speed of 42 meters per second in s-axis here, and we can see that this value occurs less than 0.9% of the time. And in fact, only 2 strong wind cases with the maximum instantaneous wind speed over 41 meters per second has been recorded during the summer since the establishment of the King Sejong stations. So recently, the Kwon et al. Investigated the characteristics of these strong wind events at King Sejong stations using the numerical model experiment and the observation data analysis. And they revealed that this strong wind event is caused by the combination effect of the downslope windstorm caused by the Antarctic Peninsula topography and the approaching of the deep cyclonic systems to the King Sejong stations. However, in their research, the effect of the topography of the Antarctic Peninsula on the occurrence of the strong wind has not quantified. So in this study, as an extension of the earlier research by them, we attempt to quantify the effect of the Antarctic Peninsula topography on a strong wind event at King Sejong stations. So for that purpose, first, we did the sensitivity analysis of the wind speed simulations to the Antarctic Peninsula terrain height by conducting a series of the polar walk simulations of 100% and 50% and 0% of the terrain height of the Antarctic Peninsula, like this. And the numerical simulations done by using the Wolf models with this kind of model setting options, and we applied 3 domains like this with the 27 kilometers and 9 kilometers and 3 kilometers horizontal resolutions. And those figure B, C, D shows the domain 3 with the different height of the Antarctic Peninsula topographies like this. And this figure shows the large-scale feature of the sea level pressures and wind field. In all experiments, we can see that the low pressure system in the north is approaching toward the King Sejong stations and the Antarctic Peninsula as time goes by, like this. And in control experiment, we can see that there is a strong deformations of the ice above field on the eastern coast of the Antarctic Peninsula, like this, on the onset stage of the strong wind event. And on the peak phase of the wind speed, these deformation become more stronger, like this.
2 minutes.
Okay, 2 minutes. Why? Okay. I'm sorry. I think maybe it's better to show the most important slide here. Yeah, and this figure shows the simulation result of the hourly mean 10-meter wind speed from the all 3 experiments and the observations. The black line shows the observations, and the other 3 colors shows the result from other 3 experiments. We can see that the control experiments, or the red line, successfully represented the observed feature in the strong wind in both terms of peak wind speed by around 94% of the observations. In contrast, the flat experiment significantly underestimated the peak wind speed by around about 50% of the observations. And the flat experiment underestimated the peak wind speed, but shows better result than the flat experiment, producing a value of the 14 meter per second. It's almost 70% of the observations. So this is the summary. I think the contents of the summary is very similar with the previous slide. Yeah. Thank you.
Thank you. You can ask questions with the Q&A facility in. So
maybe the fact we started a little bit later, we probably don't have much time. So if we start the next presentation, that'll keep us on schedule. Okay?
Yeah.
So thank you, Dr. Kwan. Appreciate your interesting results of the strong wind and impact of the peninsula. So let me move on to the next presentation. It's Sibin Simon going to talk about extreme precipitation events and associated atmospheric processes over Dronning Maudland, East Antarctica. And you have 10 minutes, and please share your screen. Thank you very much.
Yeah. Hello. Am I audible?
Yeah.
We can.
Yes. Yeah. So myself, Sibin Simon. So I'm a PhD student at National Center for Polar Ocean Research, and this is a part of my PhD work, which in collaboration with British Antarctic Survey and IIT Kharagpur, which deals with the extreme precipitation events and associated atmospheric processes over Dronning Maudland, East Antarctica. So let's start with what are extreme precipitation events. So this extreme precipitation events, or EPEs, are highly episodic, short-living, heavy precipitating events which contributing a significant amount of precipitation to the annual total precipitation within a short period of time. So why we study EPEs over Antarctica? So these EPEs are controlling year-to-year variability of snowfall across Antarctica. It's a major contributor to the surface mass balance and stability of ice sheet. And also it's a very important factor in implications which can make any reconstruction of past climate records from ice cores. The frequency, the magnitude, and the moisture source are major important factors while we should consider during the analysis of ice cores. So this is a recent study from Turner et al. 2019, which shows the importance of extreme precipitation events over total. It was in pan-Antarctic work, which the darker color shows the areas where EPs are more important. So from this study, we got inspired, and we were studying about more focused high resolution study over Dronning Maudland. For this study, we have used the criteria, EPE criteria, as the precipitation day greater than 95th percentile of all time series. So that means the top 5% is considered as EPE, and precipitation day is taken as precipitation greater than 0.02 millimeter to remove the non-precipitating days. So we focus on the spatial and temporal variability of EPEs over Dronning Maudland and associated processes for the 40-year period from 1979 to 2018. So first, coming to the spatial variability of EPEs and their contribution in Dronning Maudland region, the first figure shows the annual mean precipitation, the climatology of precipitation over Dronning Maudland, and the second figure shows the precipitation from EPEs, annual precipitation from EPEs. So with these figures, we have calculated the precipitation contribution from EPEs over the Dronning Maudland, and which in case it shows the importance with the orography of Dronning Maudland. An average of 35 to 40% of total annual precipitation is contributed by these top 5 EPEs, and the maximum values are it is very much associated with the complex orography of Dronning Maudland, and we have used the ERA 5 reanalysis for the analysis coming. So from spatial, we have analyzed the temporal variability of EPEs also. For that, we have took a near coastal location, which is called IND33, where we have ice core records. So we have picked the point location, and we found about 353 EPE days during that 40-year period with a frequency of 8 to 12 EPEs per year. And the interesting result we have got from the time series is that there is increasing trend in precipitation contribution from EPEs, although there is no increasing trend in number of EPE days. That means the events with high magnitude are increasing for the recent decades. And for the atmospheric or synoptic patterns during these EPEs, we have calculated the composite mean sea level pressure during these events. We average the synoptic pattern for these 353 EPE days, and it shows a presence of deep low pressure to the west of Dronning Maudland or IND33 location, and to the east there is a high pressure anomaly. And we also analyzed the EOF analysis of top 100 EPE events and show to get the different atmospheric patterns during EPs. And we have here shown the modes explaining 60% of variance. The first two modes shows the ridge trough ridge pattern, and the second mode shows the eastward propagation of this pattern. And third and fourth mode explains the eastward moving cyclones over north of Roni Modeland. And from figures, it's shown, it's seen like blocking high pressure to the east is an important factor in intrusion of moisture from the oceanic region to the coastal or inland region. Also, we try to answer what controls the interannual variability of EPs. So there are few years with a higher number of EPs and less number of EPs. So to answer that, we took the geopotential height anomaly over an area over north of Roni Modeland, which is 0 degrees to 35 degrees and 60 to 75 degrees. So let's look at the inland location, which is situated at 75 degrees south. So from this figure, the red line shows the geopotential height anomalies, and the blue line shows the daily precipitation. The blue horizontal line is the EP threshold. The green dot shows the EP dates. So we can clearly see that whenever there is an EP occurring, there is a positive geopotential height anomaly in that year. So we have taken 2 years, which 1 year with more number of EPs and 1 year with less number of EPs. There are only 3 EPs, but they also have a good relation with the geopotential height. So that indicates the presence of an atmospheric block over that north box. The more moisture is coming to the inland location and make precipitation EPs there. And when we look at the coastal station also, it somewhat sense of low pressures also in that box also becoming a reason for EPs over that location. And the year with less number of EPs, or it's not showing that much anomalous geopotential height, but sometimes there is atmospheric blocks without any precipitation is also there. Then from this, we can say that occurrence of atmospheric blocks in the circumpolar trough, which allows the feed of moisture to the coastal or inland location. And atmospheric blocking is more significant relation when occurrence of EPs over inland locations. Then the other question was, where does moisture come from? So we look at the integrated moisture transport for these individual events, and we found that it's coming from different directions. But although we can say the source of moisture is almost from 30 to 40 degrees south in Atlantic Ocean, and with the moisture pattern, the length, width, and the direction, we found that 56% of EPs are associated with atmospheric rivers. So especially the top 10% are atmospheric rivers. And with this, we confirm with Dr. Jonathan Willie. He provided the atmospheric river landfall dates with the integrated water vapor air detection scheme. So here we can see this is a composite for top 10% of EPs, which shows the atmospheric river like moisture transport with the help of a deep low pressure anomaly to the west and high pressure anomaly to the east of the location. And the direction of this moisture transport was not always the similar. So we tried a machine learning tool called self-organizing map, SOMs, to get the major patterns of moisture flux. With it shows the frequency of occurrence in this box. So we used integrated water vapor transport during EPs for this SOM calculation. So this box shows the frequency. So from that, we can see that the 4 boxes are more frequent occurrence patterns. So always almost all moisture flux pattern shows a high values of moisture flux from 30 to 40 degrees south in Atlantic Ocean, and it coming to the IND 33 coastal Roni Modeland from different direction with respect to the presence of low pressure, high pressure synoptic pattern. So moisture coming from different location in association with the low pressure to the west and the high pressure to the east of north of Roni Modeland. So to get an idea about what is an individual EP look like, so we have shown a case study of maximum precipitating event. This was the top precipitating event which happened on 8th November 2015, and it is a 2-day event which precipitated on 9th also, and it contributed almost around 22% of that year total annual precipitation in just 2 days. So that shows the importance of EPs. And here it was an atmospheric river event. Here we can clearly see that the moisture is always coming from It's coming from the 20 degrees south with a perfect atmospheric river-like pattern, with the presence of a deep cyclonic pressure on the west side and a blocking high ridge on the east side. Through the eastern flank of that low pressure, it coming and landfalling over the coastal region. So this is the precipitation anomaly during this event. And we can see the moisture anomalies are going further inland also. So we are trying to model this event with a high resolution polar WRF model to get the importance of orography in this landfall of such events. So that work is ongoing. So coming to the conclusions, we can see like 35 to 40% of total annual precipitation is contributed by this top 5% of EP events with a frequency of 8 to 12 EPs per year. And the topography of Trondheim Modeland has a significant role in this, the variability over EP occurrences. The low pressure to the west and the high pressure to the east is the major synoptic pattern during the EPs. Occurrence of this atmospheric blocking north of the Trondheim Modeland controls the interannual variability, especially in the interior locations. The major moisture source location for this IND 33 location is 30 degrees south to 40 degrees south in Atlantic Ocean. And from atmospheric river analysis, it's like greater than 50% of EPs are atmospheric rivers with different moisture transport pathways. So you can contact me on this email ID and you can follow at this Twitter ID. Thank you for your time. I'm open for discussions.
Okay.
Thank you, Nin. There are Q&A that you can answer on the Q&A chat. So we can let Sweta Chitela to make the presentation.
Okay. Okay, so I'm not sure I can pronounce the names correctly. Chitela Sai and Prabala Swetha, and to talk about atmospheric drivers of extreme precipitation events over Amundsen Sea embayment of West Antarctica. Once again, you have 10 minutes. I see that you're sharing your screen, so please go ahead.
Yes, thank you. Hello, everyone. I'm Chitala Sai Prabala Swetha of Coral Department under Indian Institute of Technology, Kharagpur. Today, I'm here to talk about atmospheric drivers of extreme precipitation events over Amundsen's environment of West Antarctica. So, as we all know, in the recent decades, West Antarctica lost a lot of ice, and that is happening due to vessel melting. And it can also, and we also know that like surface is also warming, and some of this mass can be compensated by the precipitation, and the precipitation is the important to understand the mass balance of the ice sheet. And this precipitation, most of the precipitation is coming from the extreme precipitation events. So to study precipitation over West Antarctica, we have used RACMO model data from 1979 to 2016. And here from the figure to the left, you can see the thick red lines, which shows my study region. And the figures to the right shows the spatial distribution of average daily precipitation and average precipitation from all EPA days, and the difference of this average precipitation from EPs and the average daily precipitation. So from here, you can see that most of the precipitation is concentrated in the coastal areas, and that is in the range from 16 to 34 mm per day. And you can see that average precipitation from all EPA days is nearly 7 times of that of the average daily precipitation. And thus, finally, like EPs contribute around 35% of the total precipitation over this domain. So that's why we are focusing a study on extreme precipitation events. In order to capture the characteristics and drivers of EPs, we have selected 2 locations in the coastal region, coastal areas, that is Ivan Small and Ware Peninsula. So this figure shows the correlation between the average daily precipitation at the Ivan Small and Ware Peninsula to this domain. From this, we can see that there is strong correlation with the precipitation over this region. And you can see that EPs at Ivan Small and Ware Peninsula contributes 41% of the total precipitation over this domain. And the frequency of occurrence of EPs at both the stations are more in winter and subsequently less in autumn, spring, and summer. So in order to identify the drivers of extreme precipitation events, we have done EWF analysis of geopotential height anomalies at 850 hectopascal. And we have considered the first 4 dominant EWF nodes. So here the figure to the left shows the spatial pattern of EOF1 mode. You can see that here an annular structure is present, which is similar to the Southern Annular Mode, which is the principal mode of atmospheric variability. And then the composite analysis was done during the EPE days of Evans mode, such that the occurrence of EPE days is only due to the presence of respective PC mode. So this figure to the right shows the composite analysis, and the shaded region shows the moisture divergence anomalies, and the arrow shows the moisture transport anomalies, and this red dotted lines and solid lines shows the geopotential height anomalies. You can see that now here in the composite analysis also, like and similar to SAM, an annular structure is present in the geopotential height anomalies, and the large moisture transport anomalies bring large moisture fluxes onto the continent over this region and converges here, which leads to extreme precipitation there. And from the table with seasonal correlation between PC1 mode and SAM, we can see that PC1 mode has a good correlation with SAM index. Moving on to the next slide, PC2 mode. Here, this figure shows the spatial pattern of EOF2 mode. Here we can see that a change in polarity is observed, like which is identical to the Emerson zero pattern as mentioned in date 2018. And the figure to the right shows the composite analysis when PC2 mode is dominant. Here you can see that a zonal shift in the geopotential height anomalies is present, and the strong moisture transport anomalies bring large moisture fluxes onto this continent over this region and converges here, and it is very intense and which leads to extreme precipitation there. And this from this figure, like this shows the composite of moisture transport anomalies. So here you can see that the moisture transport is majorly from the south of 40 degrees south. And to capture the zonal shift in the geopotential height anomalies, we define an index called ASN Lawn Index, which is the difference between the mean sea level pressure averaged over the box 1 in the Western Amazon Sea region and the box 2 as shown in this figure. So from the table, the seasonal correlation between PC2 mode and ASN Lawn Index, you can see that PC2 shares a very strong correlation with the ASN Lawn Index. And this figure shows a spatial pattern of the EOF3 mode. Here we can see that this pattern resembles the ENSO pattern, as it has like negative anomalies are present over Amazon Sea during La Nina events, and positive anomalies are present over Amazon Sea during El Nino events, as mentioned in Clement for 2013. And here this figure to the right shows the composite analysis when the PC3 mode is dominant. So here we can see that moisture convergence over here is less when compared to previous PC modes, as it has been associated with the less moisture transport anomalies. And from the seasonal correlation between PC3 mode and ENSO index, we can see that PC3 mode has significant negative correlation with ENSO index. And here, this shows the spatial pattern of EOF4 mode. Here we can see that tripolar spatial pattern is observed, like high, low, high pattern, like which is similar to atmospheric rivers. And the figure to the right shows the composite analysis of PC when PC4 mode is dominant. So we can see that moisture transport anomalies are associated with the geopotential height anomalies in an atmospheric river pattern. Like you can see that blocking structures on either side, like here and here, which shows the close proximity to the observed atmospheric river pattern, as mentioned in Billy et al. 2019. And from this, we can see that EOF4 mode shows the most favorable pattern for producing atmospheric rivers. And here the moisture, we can see from the composite of moisture transport anomalies, we can see the moisture transport is from the, you can see that it's from the mid tropics, like as a distinct band of moisture inflow from the Atlantic to this region over here. And from the relative seasonal contribution of different atmospheric modes, finally, these figures A and B like shows the seasonal distribution of EPE days occurring with respect to PC modes at Evans Station and Bear Peninsula. And the C and D shows the contribution of dominant PCs to EPEs of Evans and Bear Peninsula. So from here, we can say that like EOF2 mode, like which is the Amazon Sea long zonal pattern, is the leading driver of EPEs. And with the contribution of 40% at Evans and 49% at Bear Peninsula. And this EOF2 mode is important for EPEs during autumn, winter, and spring seasons. And EOF3 mode, which is a representative of ENSO, has 26% at Evans Mall and 18 at Bear Peninsula. And the same EOF4 mode, which is like suspected to be an atmospheric river pattern, has 23% contribution to EP at Evans Mall Station and 18% at Bear Peninsula. So on an average, like we can see that EOF4 is slightly more dominant than EOF3 mode during all the seasons, except in spring, where EOF3 is more dominant than EOF4 mode. And the EOF1 mode EOF1 mode, that is SAM, contributes the least percentage to EPA days in all the 4 seasons. And the total contribution of EOF1 to EPA days is 9% at the Evans Mall and 14% at the Bear Peninsula. So the summary of this study is that 41% of the total precipitation at both the Evans Mall and Bear Peninsula is contributed by the extreme precipitation events. And our analysis identifies the main drivers of the atmospheric variability, and this study relatively quantifies the different drivers of EPs in the West Antarctica. And zonal shift in Amundsen sea level is the important. It's important, and apart from it, the tensor forcing and atmospheric rivers are also important. Thank you.
Cool. All right. And questions should be typed into the Q&A that, and I haven't checked, but presumably there's, let's see, no open questions. Okay. So if you have any questions for our speaker, please type them in the Q&A and she can answer them offline. Okay. Thank you very much. So our next speaker is Gennady Milanevsky, and he's going to talk about comparison of planetary wave spectrum in the 2019 Antarctic SSW with the 2020 non-SSW strong vortex conditions using ozone data. Okay, Gennady, you have 10 minutes. You've shared your screen, so please go ahead.
Thank you, David. I should explain that SSW is a sudden stratospheric warming. So in our talk, we study zonal wave number spectrum of planetary waves in Antarctic atmosphere during spring ozone hole time in 2 contrasting years in 2019, when the sudden stratospheric warming take place, and 2020 is non-sudden stratospheric warming year, and when the long-lived stratospheric vortex exists. For analysis, we use satellite data from ozone monitoring instrument and ground-based Dobson observation at Vernadsky Ukrainian Antarctic Station. So we study the features of planetary waves with zonal wind numbers, mainly 1 and 2. So I remind you what is the mean sudden stratospheric warming. This primary definition of this event is requires the stratospheric temperature rising and zonal westerly, usual zonal westerly wind became weak in even reverse to easterlies at 10 hectopascal pressure level and 20 degrees latitude. So in the picture left, we see the example of the sudden stratospheric warming in Arctic in 2018, when the vortex was split into subvortices. Main source of this sudden stratospheric warming is planetary waves, which penetrate into stratosphere from troposphere, where they generated due to thermal sources or zonal flow disturbances by topography. And you see examples of resulting special disturbances in temperature and in ozone distribution. You see the planetary wave number 1. We have 1 maximum, 1 minimum, and planetary wave number 2, when we have 2 maximum, 2 minimums on zonal band, latitudinal band. These 2 events in the 2019 and 2020 is very different. In this row, you see the event of minor southern stratospheric warming. And in contrast, in spring 2020, the stratospheric polar vortex was relatively stable, and ozone hole area reached a size very close to its historical maximum. In longitude time dependencies of total ozone content, we see also difference between 2 years, left panel and right panel. And TOC variation demonstrates the contrast in ozone hole H region in these 2 years, because it's 2 pictures in close to the edge of the ozone hole in 65 degrees latitude south. On this picture, larger ozone values are shown in red, and values ozone hole levels seen in blue. And by Vernadsky-Dobson measurements, it's left plot, you see that in 2019, it's very small time when the ozone hole conditions was seen. It's only some days till 20th of September, and then we don't see ever ozone hole over Vernadsky this year. In contrast, in 2020, you see the ozone hole conditions was seen even to end of almost end of December, because it was longest time of existing ozone hole in history. In longitudinal distributions of TOC values in the right panel, which is a very big difference in asymmetry on longitude ozone distribution in these 2 years. In September 2019, this asymmetry was almost 5 times larger than in 2020. According to our spectral decomposition, we make Fourier decomposition for planetary waves components, and we see the southern stratospheric warming in 2019 take place during the peak activity of quasi-stationary planetary wave 1, its blue line, and in the same way, it's quasi-traveling wave 2, it was very active as well. So these 2 waves enhanced in one time, and they in our understanding that brings the start of southern stratospheric warming and disruption of ozone hole. In contrast, in 2020, you see the alteration of maximum and minima wave number 1 and number 2. And this confirmed possible anti-correlation of the amplitudes, and probably this indicates the redistribution of energy between different spectral components of planetary wave. We also check the wave numbers from 1 to 5 on these 3 graphs. One row we have the September, October, and November, and the relative contribution of each wave number is very different in 2019 and 2020, but relative contribution of the wave numbers 3 to 5, it's very small and not more than 0.1. Very different evolution planetary waves was seen in November, because in November 2019, it's a planetary wave 1 amplitude is dropped down very sharply, but in 2020 it was seen very long time, as I said, until December. Its vortex persisted in 20th of December. So I come to conclusions. According our spectral decomposition planetary wave, in 2019, southern stratospheric warming take place under dominant influence of quasi-stationary wave 1, which was enhanced by influence of traveling wave 2. In contrast, weak wave 1 in spring 2020 allowed polar vortex to be relatively stable, and in spite of regular periods when traveling wave 2 provided significant contributions. So we see the anti-correlation between wave 1 and wave 2 in 2020, and which presumably indicates that planetary wave energy transferred between these different spectral wave components like processes in 2019. So this analysis maybe helps to understand what are the reasons of sudden stratospheric warming in stratosphere, and it is necessary to receive some preconditions of these events. Thank you for attention.
Okay. Thank you, Gennady. All right. So we have some time set aside now for online discussion of the preceding papers. So probably, Adriana, you'll modulate that, and let's see if we can, how should we do this? Should people put their questions in the Q&A, and then we can ask them to read them and the speaker to respond to them? How about that?
Yeah. Yeah. If there are any questions that from the previous papers that haven't been answered right now in the Q&A, please write it down. And so okay, so I think everything was crystal clear, and we can move on with the next paper.
Okay. Okay. Hope everybody, yes, all right. Okay, so we're a little bit ahead of time, just for everybody's reference, which is great. Okay, so Guitao Shi, apologize for any mispronunciation. The title, Can the Prolonged Period of Stratospheric Ozone Depletion be Recorded in Antarctic Snow? And please share your screen, and you have 10 minutes. So please go ahead. All right. We've got your text box on the bottom that we can see. So
all clear. Hear me?
yes, we can hear you now.
Okay, okay, great. Okay.
And
hello,
maybe I think you need to make it full screen.
In presentation mode.
Presentation mode.
Yeah.
Okay, now it's okay.
Not.
It's very small. You can see.
Very small. Okay, I try to.
Ma'am, can you move to presentation mode, please? Sir, can you move to presentation, please? Slideshow.
I will try to share again for this.
Okay.
I'm not sure whether it is okay now.
So can you make it into slideshow or full screen?
I don't know. Is the full screen now?
No, sir.
No.
No. Okay, I don't know what's wrong with it. I will try.
Can you
again.
try sharing again?
Okay, yes, I will try. Try my. Okay. Oh, I'm not sure why.
All right. Well,
It'll work?
it's not.
It's good?
We just have a blank screen at the moment. We had your, just 30 seconds ago, we had your.
Sir, can you remove the window in front of your presentation, please?
Okay, so I'm sorry, waiting for 1 minute. I will try again. I'm not sure why there is a problem for this.
Ma'am, can we move to the next speaker in case, meanwhile, let's try to figure out.
I will try again. I'm not sure whether it works now.
Oh, we can, no, it's in the same. We can proceed with a small, not in presentation mode, and so you can give your talk anyway. How about that?
Okay.
Well, you can start.
I'll stop now.
Start, please.
Okay.
So, Adriana, I'm not sure whether it is possible to move the next. Maybe I'd like to restart my computer. I'm not sure. What's the problem?
Okay, maybe what we should do is move on to the next presentation.
Okay, I will
And,
restart my computer.
and maybe discuss this with the technical people. Maybe they can help you, and we can come back to see if we can solve your problem. Okay?
Yeah. Okay, I'm sorry. Thank you.
Okay, very good. Technical problems. Okay, always happens. Okay, so let's see. Are we ready to go with, let me see here. Do we have Nehu Salim online? Or is it a little bit too early? Maybe not. This might be a little bit okay. Yeah, it's probably a little bit early. I mean, we are 15 minutes ahead because of this. Okay. So we could probably take, what do you think, Adriana? Maybe take a 5-minute break,
Okay.
and then we could come back at the
In 5
top of the
minutes.
hour.
Yeah. Okay.
We got to adapt to life as it is. You know that?
Yeah. Like in Antarctica.
Yeah, that's right. So maybe so at 12 UTC, everybody, we'll be right back after a short break. So you can go and stretch your legs, and we will resume at that time with Dr. Salem's presentation on the marine boundary layer. Okay, so 5-minute break.
We're back.
So, Adriana, you have to promote people to presenters, is that right? Or panelists?
Yes, but we are trying to find Dr. Neha Salem, but we cannot. So maybe we can move up to Dr. Shang, because I cannot either the IT team can find Dr. Salem. So I'm afraid we have to move on.
Okay, all right.
Yeah,
looks
okay,
like-
fine for me.
Okay. No. Okay. All right. So you're the gentleman going to talk about the thermodynamic characteristics of the marine boundary layer over the
Yes, sir.
Indian Ocean sector of the Southern Ocean. Is that right?
Sorry, maybe Dr.
I'm Neha.
Shaikh is already here, but with another name. Are you?
Hello.
Hello.
Neha Sheikh. Yeah, Neha Salim.
Okay, so I see you with another name, sorry, Shaikh. So sorry for the misunderstanding. So sorry, Dr. Shang. We can hear Dr. Salem. So we start with Dr. Salem.
Shall I share my screen?
Thank you. Can you share your screen, please?
Yeah. I'll start. Hello, everyone. A very good evening to all the respected members. My name is Sheikh and I'm a PhD student at the university. As you all can rightly see from the image picture on the right side of the slide, that today I'll be discussing some of the unique observations that have obtained on the atmospheric boundary layer structure over the Indian Ocean sector of Southern Ocean. And these observations are obtained using set of high resolution atmospheric soundings that were released in this sector of Southern Ocean. We all know that climate is drastically changing, and there are many clear indicators indicating the same, such as global warming, increasing air temperatures, extreme heat events, and many more. Whereas the contribution of Southern Ocean to this change is of significant importance because Southern Ocean is likely estimated to uptake nearly 70% of the globally released heat content, as well as it acts as a strong sink for globally released carbon dioxide. For those who are less familiar with Southern Ocean, it is the region that lies between these two yellow marked circles. As we can clearly see that this ocean is formed by massive water masses that continuously circulate around Antarctic strongly interconnects three major global oceans: the Pacific Ocean, Atlantic Ocean, and Indian Ocean. So we can clearly see that this region forms an intermediate regions with that over the interactions occurring in the polar region. But despite of its significant role in climate change, this region is one of the least explored regions because of its extreme remoteness and harsh weather conditions. Recent explorations have revealed that some unique observations on the dynamic atmosphere that is prevailing over this region, but those reports are mainly available from the Australian sector and the African sector. However, the atmosphere over the Indian Ocean sector of Southern Ocean is least explored. So that is what I'm trying to present in my study. As we all know that in the complete structure of atmosphere, the layer that is of crucial importance is the atmospheric boundary layer. And this was the picture which was taken at 64 degrees south. And we can clearly see that there is a thick band of cloud followed by some sort of inversion that is clearly separating the free tropospheric air from the air mass that is there within the atmospheric boundary layer. And the factor that is governing the dynamics of this atmospheric boundary layer is the strong air-sea interaction that is occurring near the surface. And this air-sea interaction differs region to region is the governing factor for the stability structure of MABL, nature of clouds, inversions, and the dominant processes that will drive the structure of MABL over different regions across the globe. So hereafter, I'll be discussing on this 5 major characteristics of MABL of Indian sector of Southern Ocean. To achieve that, I have participated in 3 campaigns conducted over Southern Ocean during the austral summers of 2017, 2018, and 2020. Wherein we have successfully sampled this region of Southern Ocean across by traversing this fronts. And this is the cruise track that we have followed, where continuous measurements were taken during the forward track, longitudinal transient track, and the return track. To understand the structure of MABL, the primary data set that we have used is the surface meteorological measurements and collection of 75 high-resolution atmospheric measurements to understand the vertical meteorology over this region. So this was the major frontal regions that we have crossed during the 3 campaigns. And the figure on the right-hand side of this slide, we can see that the variation of crucial meteorological parameters, that is temperature, humidity, wind speed, and wind direction. We can see that this meteorological condition shows sharp spatial variation as well as variation in the vertical 5-kilometer air column. And these variations were specifically distinct over each of these frontal regions. And as a result, I'm trying to understand the structure of boundary layer over each of these fronts. So to begin with the air-sea coupling, for that I have used the air-sea temperature gradient that was observed over each of the front, as well as I have taken mean sea level pressure. Then to understand the vertical stability conditions, I have used 2 conserved variables, that is virtual potential temperature and water vapor mixing ratio. I've used conserved variable because of the tendency to remain conserved during dry adiabatic movement of air masses. So what this conserved variable will give us is that in case of unstable atmospheric condition, this theta V and R seems to very nearly uniform, indicating presence of uniform mixing and formation of well-mixed layer. But in case of highly stable atmospheric condition, the tendency of theta V shows an increasing tendency with increasing height. So with this basis, what I observe is that from NSTF1 to SAF region, on an average, high positive sea temperature gradient and high mean sea level pressure has accounted for higher destabilization of lower atmosphere. And here we have observed deeper well-mixed layer structure. But moving towards the southernmost extent from polar front to coastal Antarctic, on an average, we observe a negative air-sea temperature gradient and decreasing mean sea level pressure. And the coupled effect of this is clearly seen in the highly stabilized condition of the atmosphere with from the increasing profiles of theta V, which is constantly observed in from polar front region to coastal Antarctica. So depending upon the destabilized conditions observed on an average over these regions and highly stabilized conditions observed over this region, I've tried to understand the nature of clouds
So here, this image represents the frequency of cloud occurrences, whether there is a single cloud layer, multiple cloud layer, or complete cloud layer structure. Whereas this image shows the base of the first cloud layer and the top of the second cloud layer and the total geometric thickness of the observed cloud. So what I observe is that in the regions where highly destabilized conditions were there, prominent no cloud layers were observed, followed by single cloud layer. And the height of the single cloud layers were at higher altitudes and were thin in total geometric thickness. But interestingly, the regions where highly stabilized conditions were there, I observed more than 2-layered clouds were commonly observed, as well as complete cloud layer was also observed. And interestingly, over this region, the height of the cloud layer, where clouds were as low as 500 meters, which was taken as a threshold for estimating the cloud base height. And the cloud top height were as high as 3.5 kilometers also. Interestingly, significant thick cloud layers were observed over these regions. Another unique feature that is observed is that over these regions where highly stabilized conditions, multi-layered thick clouds were there. Those clouds are likely to be in the form of supercooled liquid phase, as well as at higher altitudes, they are likely to be in the form of ice phase. Moving towards the inversions, the regions where highly destabilized conditions were there, I observed presence of more than 3 inversions, and these inversions were at relatively lower level, whereas in the region where high stabilized conditions were there, the inversions were at higher altitude. And interestingly, the inversions of significant strength were observed over polar front region because of the action of the strong wind shear induced by high speed winds. Then signatures of dominant atmospheric processes, I have tried using conserved variable analysis. And what I observe is that the regions where highly destabilized conditions were there, convective mixing was a dominant process at lower altitudes, and whereas at higher altitudes, radiative warming was prominent. But in regions where highly stabilized conditions were there, signatures of precipitation were dominant. But in these regions, the condensation of falling precipitation was supported by advection of cold winds, and these condensation were likely in the form of snow and fog, which were visually inspected during the campaign. However, over coastal Antarctica, at low level precipitation was dominant, but at higher level, radiative warming as well as sublimation supporting sort of Virga condition were also observed in some of the soundings. So here, some of the key findings are represented using a schematic, which shows that at regions with highly destabilized condition, low level inversions and thin cloud layers were there, whereas at highly stabilized conditions, low level multi-layered clouds in mixed phase and high level multiple inversions were prominent. Thank you.
Thank you.
Okay. Okay. So questions for our speaker should be typed into the Q&A so she can answer offline, I think, as we're having a little bit of trouble with your audio and the internet connection. But thank you for your presentation, very interesting. Okay, so let's move on to the next speaker, which I think is available. Xiaohui Sheng, talking about the near ground stable atmosphere and strong in temperature inversion monitored at Dome A, Antarctica. And please share your screen. And once again, you have 10 minutes. Thank you very much.
Okay, thank you. All right. Can you see my full screen?
Not the full screen. It's not in
Hold
presentation.
Yeah, hold on for a second.
Yeah.
All right, how about now?
Nope. the IT people said, stop sharing screen, put it in presentation mode, and then share your screen. So how about trying that?
Okay.
You can choose it with the Alt Tab functionality if you. Great. Now
Okay.
it is.
How about
Thank you.
now?
Yeah, it's good. It's good.
Okay, thank you. Sorry about that. First, I want to thank the organizers for giving me this special opportunity to share with you our work and data. This is special because I come from astronomy community, which may sound strange. So first, why do we astronomers care about the atmosphere? One of the reasons is because atmospheric turbulence causes astronomical seeing, which is smears images. That's why we see twinkling stars, which is bad for astronomy. We always want to have some sharp images. At Dome, we found that the turbulence is mostly within the boundary layer, which has a median thickness of only 14 meters. So above that boundary layer, we are supposed to have very stable, free atmosphere and very good seeing. On the other hand, weather data are very important for us to operate telescopes in winter, because Kunlun Station at Dome is still not a winter over station. So all our instruments have to be unattended in winter. Although they got support from Plato with power and satellite communication. So we built our first MAT called Kunlun Automatic Weather Station in 2011. It's 50 meters tall. We placed many sensors at different heights, including one temperature sensor below the ice surface at 1 meter depth. The plot shows all the temperature data with all the data of the temperature at different heights with different color. From that data,
we are seeing
actually
the same slide. You are not changing slides, right? Or are you?
I did.
Oh no, we just we're seeing the first one. Why do astronomers care about the atmosphere?
Really?
Yeah.
Oh.
That's why. Sorry, but I thought you were passing slides. We are not seeing that.
Let me try to stop sharing again and restart.
Okay.
Sorry about that.
Yes, now we are seeing yeah.
Okay, did you see this one?
Yes.
Okay. So basically we want a very stable atmosphere so that we can get very good seeing and get very sharp images. So we built this mat, 50 meters tall, and we placed many sensors at different heights. And the plot shows the data of the temperatures at different heights with different colors. So using that data, we got, we did confirm there's a very strong temperature inversion. The temperature differences can be as large as 20 degrees from 10 meters to the surface, to the ice surface. And they usually last very long, like a week or longer. We also find that the strong temperature inversion, when the temperature inversion is stronger, the boundary layer is thinner, and that is expected. So the bottom plot shows the windrows at 3 heights. Usually, generally the wind speed is very low at Domei. At 4 meters high, we got a mean wind speed of only 1.5 meters per second in 2011. But that tower fell down after a year, so we built another one, and we were able to, we managed to operate this one for continuously for 20 months. And that plot shows all the temperature data for that period. The tower is similar to the first one with many sensors. And we basically, from the data of this tower, we basically confirmed what we saw from the previous instrument. There's still strong temperature inversion. The histogram shows for more than 90% of the time, there exists the temperature inversion, and the temperature difference again can be as large as 20 degrees from 10 meters to the surface. And the median value is about 5 degrees. And we plot the median temperature of each month for different heights for the entire year of 2015. And you can see during the summer, the temperature inversion is higher, is stronger. And we also plot the wind speed at the bottom. The different color also corresponds to different heights. So there's a clear evidence of the laminar flows. That tower also was broken, was broken after 20 months. But fortunately, we were left with part of it. So we repaired the tower and managed to operate for another 17 months, but only with sensors up to 4 meters. And that shows the data, the temperature data of that period. So basically, with all the data, we confirmed what we found from the previous years. And in 2019, we built a brand new tower, but for some complicated and unfortunate reasons, we had to shut it down after 3 months. But we have planned to revive it if we go to Domei again. So if we put all the data together, we can look at the annual variation. This shows the temperatures at 4 meters and 14 meters for several years. Basically, the temperature, the seasonal change is similar, except for the first year, except for 2011. And we believe that's real. We checked the sensors and we believe that's real. The difference also seen in the wind speed seasonal variation. And 2011 still shows a different pattern than the other years. For the wind speed, the annual variation is a little bit larger compared to the temperature. And also it changes, the annual variation is much larger for if you go higher, like 14 meters.
2 minutes.
Okay. So we use this data to confirm that we do have very stable atmosphere at Domei, and we managed to measure the scene directly using small telescopes called DIM. So if you look at the up left corner, when the boundary layer is below the 8-meter tower, we can get very nice, this peak, the sharp peak, very nice, very good scene. But if the boundary layer is above our tower, the scene, the ABL scene is not that great. We also find that the scene gets better if we have a stronger temperature inversion. So the statistics show at 8 meters, there's a 30% of chance we can get the great seeing. But combined with the weather data, we can derive that we confirmed that the boundary layer is below 14 meters for half of the time. That means if we put a telescope at about above the 14 meters, we can get the great seeing for about half of the time. And also combined with many other data, we have demonstrated that Dome has the best observing conditions on the Earth for optical, infrared, and sub-millimeter astronomy observations. So here's the brief summary. So we have multi-year continuous data for many months, and we have did simple analysis and astronomical applications. I personally believe this data set could be useful for the meteorology community, and that's basically why I'm here. We put the data at that website. You can download. The new data after 2018 will be added soon. One thing to be careful is if you do want to use the data, you need to be aware of some possible problems like the frozen anemometers. Where we discussed this in details in our papers. Thank you.
Okay, thank you very much. Okay, so once again, please type your questions into the Q&A, and that can be answered offline, or we probably will have a little bit of discussion time at the end of the presentations. So let's go to David Mikolajczyk, who's going to talk about regional warming event in winter on the Ross Ice Shelf, Antarctica, as observed by UW-Madison automatic weather stations. So Dave, when you're ready, please share your screen. You've got 10 minutes, as you know.
Okay. Hello, everyone. Oh, let me start my video too here. It's upside down. Just going to stop the video. That's kind of weird. Okay. Hopefully you can see my screen.
Yep.
We can.
All right. And I'm just making sure I can advance. Okay, there we go. All right. So I will be talking about a regional warming event on the Ross Ice Shelf. And so a regional warming event is a warming event that was observed by an automatic weather station that showed a temperature increase of 30 degrees Celsius or greater in 5 or fewer days. And to be regional, there needed to be more than one automatic weather station that observed a warming event in the same region at the same time. And so there was a warming event that occurred from 12 to 15 July 2007. On the Ross Ice Shelf, Antarctica. And that warming event can be seen in the bottom time series of temperature at one of our automatic weather stations. That's showing temperature for the month of July. And in the middle of the month there, you can see a rapid increase in the temperature. So the data that I've already mentioned, we were looking at the data from our automatic weather station network that we have on the continent. We at the University of Wisconsin-Madison, operate a network of about 60 weather stations. The map on the right shows all known automatic weather stations on the continent. The red triangles are ones that we manage. And the map on the left is kind of showing the study region for this talk, the Ross Ice Shelf there in the center. And there's approximately, I think there were around 20 automatic weather stations on the Ross Ice Shelf in July 2007, and 14 of those observed warming during this time period. And so I'll be going through some ERA interim and ERA 5 reanalysis data. I won't be talking about showing any satellite composite imagery, but I will kind of go through what made up this warming event and try to determine some causes and mechanisms for the warming. And also I will say this is the this work I'm presenting here is the culmination of my master's that I just completed this past spring. So these graphs are a time series of the 14 automatic weather stations that observed warming events. In the upper left is temperature, upper right is pressure, lower left is wind speed, lower right is wind direction. So in general, they all observed very similar temperature and pressure patterns during this event. So that in itself kind of suggests that there's one overall common mechanism that led to the warming. The wind speed and direction were, well, the wind speeds were slightly variable between the different automatic weather stations. For some of them, the wind speeds increased during the warming event. For others, the wind speeds remained calm. But for a lot of them, the wind directions were pretty steady throughout the warming event. And here is a map zoomed in on the Ross Ice Shelf with the South Pole at the top of the map. And this is showing the different automatic weather stations that observe the warming. Most of them are located either in the center or on the western edge of the Ross Ice Shelf. But the dots here are colored by when the warming event began and when the warming event began. So the lighter the color, the earlier the warming event. So in general, the warming started on the eastern side of the Ross Ice Shelf and then progressed westward. So here's a general schematic of the different atmospheric patterns that made up the synoptic scale environment before the warming event occurred. So this is a map of air interim data. The black contours are mean sea level pressure. The color fill is temperature at 2 meters. And there was a stationary low in the northern Ross Sea that was that in composite plots was pretty much stationary for the first around 5 days leading up to this event. And with that warm northerly flow just downstream of that, and a strong cold pool that was persistent over the Ross Ice Shelf, there was a large temperature gradient that was established just north of West Antarctica. And also to note, in upstream of the Ross Sea, there's a region of active cyclogenesis and cyclone sustenance, at least, off of the Adelie Land coast. And so the stationary low in the Ross Sea, those cyclones that were coming off the Adelie coast interacted with the low in the Ross Sea, and eventually there was one that appeared to be strong enough to progress the surface cyclone southward towards the Ross Ice Shelf. So I'll just go over some kind of large scale and down to smaller scale discussions of the different meteorological environments that during this warming event. So here is air interim. Here's some composites during the event, showing on the left air interim 500 hectopascal composite geopotential height anomalies. So that the dashed is negative height anomalies. The solid contours are positive anomalies. So there's a pretty evident low, high, low setup here that occurred during this warming event, with the low in the Ross Sea. And on the right is composite 2 meter temperature anomalies and composite mean sea level pressure. So one thing to note is that the mean sea level pressure composite there is southward and closer to the Ross Ice Shelf as compared to the 500 hectopascal low in just north of that in the Ross Sea. Also, there's a strong 2 meter temperature, warm 2 meter temperature anomalies over both West Antarctica and over the Ross Ice Shelf during the event. So there was a strong cold pool, as I mentioned before, that developed over the Ross Ice Shelf. So these plots on the right are showing air interim vertical temperature profiles at Elaine, which is at the far southern end of the Ross Ice Shelf. And so I chose this both because pretty much all of the weather stations showed very strong temperature inversions, but Elaine showed a strong one, and it's also furthest away from the influence of the cyclone. So I wanted to kind of use that as a way to just illustrate that this is occurring over the whole Ross Ice Shelf. So the temperature inversion here, and this isn't exactly when, since this is 6 hourly reanalysis data, it's not exactly when the warming event began, but at this time, the temperature inversion was 16.8 degrees Celsius. So that's less than 30 degrees Celsius. Therefore, it can't account, simple mixing out of the inversion alone can't account for all of the warming. And the plot on the bottom right shows the warming throughout most of the lowest 500 to 400 hectopascals of the atmosphere that occurred at Elaine. And to discuss the cyclones off the Adelie coast, there were, leading up to the warming event, there were 2 cyclones that had progressed along the coast. The first of which, a couple days before the warming event began, is shown in the plot on the left. The black contours are mean sea level pressure, and the fill pattern is 850 hectopascal relative vorticity, with only the negative cyclonic values plotted here. So the plot on the right shows 1 day prior to the event, and this is just illustrating that the cyclone 2 days prior was weaker than the cyclone 1 day prior, and that cyclone 1 day prior that eventually merged with the cyclone in the Ross Sea led to the southward propagation. This is showing the warm front. This is in the middle of the warming event, zoomed in on the Ross Ice Shelf, showing again the, well, this is showing 850 geopotential height and relative vorticity, and just a pretty classic example of the warm frontal axis going across the Ross Ice Shelf. So prior to the event, there was a stationary wave train that led to a buildup of 2-meter temperature anomalies north of the Ross Sea. And there were calm atmospheric conditions over the Ross Ice Shelf. And so with this warm pool and cold pool development, there was a strong baroclinic zone that developed. And there was the merging of the Adelie Land cyclone into the Ross Sea that led to southward propagation, and with mixing out of the inversion, warm air advection, and increased cloud cover and winds, that appeared to lead to this strong warming event. And so my goal for future work is to kind of tease out the different components of this warming, and also try to get some studies of larger scale influence on warming events over the Ross Ice Shelf, as well as in other areas in Antarctica. So thank you very much.
Okay, thank you, David. All right, so please type questions into the Q&A for David. And we're going to go back to Dr. Shi. And so let's see, you were going to talk about, can prolonged stratospheric ozone depletion be recorded in Antarctic snow? And we can't yet see your full screen. So let's.
Okay, I will try to.
According to the IT team, you have to, yes.
You can see now?
Yep.
Yes.
Okay, it's good. Okay, I'm sorry for the technical issues. So, hello everyone. Thanks to the convener of the session, David and Adriana. I am Gui Taoshi from East China Normal University, and I'm mainly focused on snow chemistry. Today I will talk about whether Antarctic ozone hole can be recorded by the snow chemicals. In the atmosphere, more than 90% of the ozone is distributed in the stratosphere. Ozone layer plays an important role in climate and surface ecosystem. It can absorb most of the sun's UV radiation, protecting the human and other living things on the Earth. In addition, because it absorbs the UV radiation, directly affects the stratosphere temperature and consequently atmospheric circulation and the Earth's climate. During the past decades, significant ozone hole occurs over Antarctic. The spring total column ozone decreased significantly from 1960 to 2000. This caused a serious climate effects. For instance, stratospheric cooling during 1979 to 1997 was observed. This was thought to be driven by decreasing stratospheric ozone. In addition, the Southern Ocean surface warms over large areas as a consequence of ozone depletion. Due to the influence of stratospheric ozone on the environment and climate, it is of interest to construct past changes in stratospheric ozone and to assess its response and feedback to climate change. Finding an ideal proxy is the most important step. Nitrate is one of the major chemical species in Antarctic snow. It can undergo UV photolysis at the surface of snow ice grains, and the photoproducts are mainly the NO2. Thus, nitrate is closely associated with near surface UV radiation levels and the column ozone. Nitrate has nitrogen and oxygen stable isotopes. Delta N15 will be enriched with the photolytic loss of nitrate, but delta O18 and capital delta O17 show distinct trends, which is mainly due to the exchange reactions of oxygen atoms during photolysis. Our previous observations at Dame also suggest the same isotope effects. Thus, isotope of nitrate can indicate the extent of snow nitrate photolysis, and then the information on the near surface UV levels and the column ozone. Snow nitrate photolysis is influenced by several factors. First is the snow accumulation rate. At the low snow accumulation size, snow nitrate can spend years in the photic zone where it will undergo photolytic processing. A close relationship was observed between snow accumulation rate and photolysis extent. The second is the total column ozone, which determines the surface UV levels. Therefore, at a site with snow accumulation keep steady, the changes in the degree of nitrate photolysis can indicate total column ozone. Snow nitrate photolysis is most significant in low snow accumulation size. Thus, the changes in total column ozone influencing nitrate may be more evident in low snow accumulation size. Dame is one of the lowest snow accumulation rate site on Antarctic Plateau. It is an ideal site for examining the relationship between total column ozone and snow nitrate. So we collected 4 snow pits at Dame with the depths ranging from 300 to 450 centimeters. We used the non-sea salt sulfate and the beta activity to date the snow pit. The non-sea salt sulfate can indicate the volcanic eruption emissions, and the basal age is around 1960s. Here, we only focus on the period between 1960 to 2000, where the total column ozone decreased rapidly. Okay, here we can see the 4 nitrate concentration series all show significant decreasing trend, decreased from about 20 nanogram per gram in 1960s to about 10 nanogram per gram in 2000. This may be associated with the changes in the South streams and all the extent of photolysis. In the following, we will examine which factor dominates the trends. Okay, first, we examine the South streams. In Antarctic, nitrate has 2 main sources. One is the long-range transport
from mid-low latitudes, and the second is stratospheric impulse. These two sources has distinct delta N15 values. The emission of NOx, the precursors of nitrate, in the southern hemisphere was increasing during 1970 to 2000. In this case, the decreasing stratospheric impulse are needed to explain the observed trends in nitrate concentrations. However, a marked decrease in stratospheric nitrate impulse is expected to decrease delta N15 values in snow, considering that the stratospheric nitrate features very high delta N15 values. But the data here, delta N15 value, show the opposite. Thus, the decreasing trend in nitrate during 1960s to 2000 is unlikely to be associated with changes in south streams, maybe dominated by snow photolysis. Indeed, we can see that with a decreasing trend in nitrate, delta N15 values increase and oxygen isotope of nitrate decreasing. These patterns are identical to the expectations of enhanced snow nitrate photolysis. Thus, the trends of nitrate is as a result of a higher degree of nitrate photolysis. Several factors can influence the degree of snow nitrate photolysis, including the impurity concentrations, snow accumulation rate, and surface UV levels. We can see that the impurity concentrations and the snow accumulation rate during this period show no prolonged trends. Thus, the changes in the extent of nitrate photolysis is unlikely dominated by these factors. And the changes in the surface UV radiation levels may be responsible for the extent of snow nitrate photolysis. Indeed, we can see that springtime 2-2 column ozone over Antarctic plateau decreased significantly from 350 DU in 1960 to 200 DU in 2000. The decrease in 2-2 column ozone leads to the higher levels of surface UV and consequently the higher degree of nitrate photolysis. Using a snow nitrate photolysis model, 2-2 column ozone is taken as a variable by keeping the other factors steady. Then the observed trends in nitrate resulting from decreasing 2-2 column ozone during this period can be simulated. We can see that the observed trends can be largely accounted for by the simulations. That is, the observed trends in nitrate and domain are best explained as enhanced snow nitrate photolysis as a result of prolonged decrease in 2-2 column ozone during 1960 to 2000. The long-term trend in 2-2 column ozone and the surface UV levels can be indicated by nitrate and its isotopes. That's all. Thank you very much.
Okay, thank you. Glad it worked out this time.
Thank you.
Okay, so we have about 10 minutes to go before the scheduled end of our very interesting session. Is there any questions for our speakers? Please type them in the Q&A, and then we'll Adriana will prompt the questions to be, well, she can read them out, and then the authors can respond. So let's see if we have any discussion. Okay. Maybe I can ask Dr. Shi one question. Okay.
Okay, I can hear you, David.
Yes, good. All right, so the total ozone concentration went down until the late 1990s and has been sort of slowly recovering since. Do you have plans to do more work looking, for example, at this change in the trend of the total column ozone and its expression in the surface snow at Dome?
Yes, a very good question, David. Yeah, exactly. In the upper layer, in the upper 90 centimeters, because the sunlight can penetrate about 19 centimeters. So that means that in the upper 19 centimeters is covered the period from 2000 and to 2020. So maybe in the future we will look at the exactly relationship between nitrate and the total column ozone. Yeah, because now it's just the snow accumulation rate at Dome is extremely low. Yeah, that's the reason. The upper part is still undergoing the photolysis. Yeah.
I see.
Yes.
Thank you.
There's a Q&A in the chat. It says the duration of the UV increase is only 1 to 2 months. How is this effective to decrease nitrate?
Pardon? Pardon?
Yes, so you can read it in the Q&A. Actually, you can read the question. The duration of the UV increase is.
Oh yeah, there is a question here. Okay.
Yeah.
Duration.
So you can answer.
Increase is only 1 to 2 months. How is effective decrease? Okay. Yes, it's a very good question. And yeah, exactly, the UV increase is mainly occurs around September to November. Yeah, but in Antarctic, the photolysis of nitrate is the most obvious during these months. So then that is the decrease in the increase the UV radiation can affect the nitrate photolysis significantly. Yeah.
Okay.
There's another one. Interesting talk. I'm interested in the role of surf winds.
That looks like for David Mikolajczyk. I think that's the warming event.
Yeah.
Yep. Okay.
Yeah. Hi, Tom. Thanks. So for most of the warming events that happen on the Ross Ice Shelf, it appeared that there was an increase in surface winds. I want to look more closely at reanalysis data for that, but of course, the lowest model level for winds is at 10 meters, I believe, and these weather stations are at more like 2 meters, so the winds will be a little different there. But for other locations on the continent, it's not always the case that there's an increase in wind speeds and then you get the warming. Sometimes the winds are steady or decrease, but you'll still have warming. So that's probably more so cloud cover that will affect those warming events. And I see another one that just came now from Jorge. I hope that answers your question, Tom.
Okay, so David, you do have that question from Jorge Carrasco. Do you know if these events have been increasing, and what is the role of atmospheric rivers in this area, if any, and what are the impacts on ice?
Jorge, unfortunately, I don't know the answer to any of those, but those are definitely interesting questions that I'd like to know the answer to. So I want to do more, I want to expand more on my research that I've done looking at years like 2002 to 2018 of warming events around the continent, and see if I can get any sort of semblance of rate of change for the warming events.
Okay. Okay. Any more questions for our speakers? Okay. Okay. I've got one for Dr. Shang, if he's still online. I'm not sure. Okay. Okay, so one application I've thought about for the profiles at DOME is for the numerical weather prediction models, which predict the, how the temperature, wind, everything varies with height. The vertical resolution is not particularly good. Typically they have the first level at maybe 10 meters. So that's sort of at the top of your inversion layer in many cases. But they do solve for the snow surface temperature. So that would be one application I could think about.
Thank you. Yeah, I basically we are not doing. We are astronomers, so I'm not really familiar with the meteorology area. That's why I'm here to present the data, and people who are interested in using them are all welcome to download the data.
So one other question that I had for you while we're talking. You seem to have some difficulty with the stability of your tower. Your tower didn't stand up for very long, it depended on the. So the US Automatic Weather Station program has experience with a 30-meter tower down on the Ross Ice Shelf, which has been there for years, actually. So people know how to build towers. What was the reason, do you think, that the tower wasn't very stable?
So our towers were kind of simple. One of the reasons one tower fell down just because one of the guy wire broke. We basically fixed that problem permanently. So the current tower should be fine, although we haven't seen it for about 3 years.
Okay.
Yeah.
All right.
So yeah, we found the problem, and we think we fixed all of them.
And
I see.
if I may jump in on behalf of our automatic weather station network, yeah, we have our 30-meter tall tower on the Ross Ice Shelf, and we have found that it needs yearly visits to at least maintain the guy wires and make sure that the tension is appropriate and everything. So so yeah, I worry that waiting longer than that would kind of lead to some destabilization of the tower, but.
Okay, thank you. But at Dome, it's not a winter over station, so we have nobody there for most time of the year. So that could be a problem for us. But we think we have fixed the problems. Thank you.
Okay. All right. Okay. Then we're at the end of this very interesting session. I want to thank all the speakers for their bearing with us and keeping to time. And we do have another session coming up in about 2 hours from now at 1500 UTC. And Adriana Gulisano will be chair of that session. So hope you can join us at that time. And once again, thanks to everybody for their participation. Hope you enjoyed it, listening to the latest on Antarctic meteorology. Okay. Thanks, everybody. Bye-bye.
Okay. Thank you.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Thank you.
Bye-bye. Thank you.
Okay.
Thanks a lot, Adriana.
Okay. See you in a couple of hours.
Absolutely. Got to be ready for unexpected developments here.
Okay. Hopefully no. Let's hope not.
We'll see.
Yeah, we'll see.
Okay. Bye-bye.
Bye.